let's go on to the next part of your quantum physics. So whatever I'm going to explain is actually going to be from this part, page 6 to page 9. So I'm just going to start explaining for this part here. So to make the explanation easier, I'm just going to refer back to this one, the picture that I just sent to your chat group. All right. So you just refer to that. That one will make your life a lot easier. If you want to copy, you copy from that picture there. You don't need to strain yourself to rush and copy whatever I've written here. All right. Okay, so let's just start. Now, in chemistry, you guys learned before that electrons have energy levels, right? They tell you that in the model of an atom, you have a positive nucleus with electrons orbiting around it, right? And when you have electrons orbiting, your electrons are orbiting in different shells, isn't it? So when you're talking about the energy levels of the electrons, now first thing first, the electrons that are orbiting around your nucleus actually have energy. Why do we say that your electrons have energy in the first place? Is because when your electrons are moving, they have Ke. And also, when you're talking about your electrons is by right negatively charged, right? So it's going to experience some form of electrostatic attraction with your nucleus. So there's force here, there's electrostatic attraction with your nucleus, there's going to be Pe here. So the fact that your electron has Ke and Pe here will tell you that your electron has energy here. Okay, so each electron that is orbiting around your nucleus will have a certain value of energy associated with them, because they're all at different distances, they're all moving at different speeds. But when you're talking about the energy levels of the electrons, we will tell you that the energy levels of the electron are specific or discrete. If, say, you wanted to represent the energy levels of the electrons in the form of lines, it will look something like this, where each line represents a specific energy level. We call this discrete energy levels. Discrete here means fixed or specific. There are no values in between. When we say something is discrete, it just simply means this now. Okay, it is fixed, it is specific, no values in between. That is what we mean by discrete. Your electron does not have a range of values like this all the way to here. No, it only has certain values in between. No other values other than the values that are indicated with the arrow here. That's what we mean by discrete energy levels. Okay, so just note that for your case here, electrons have specific energy levels or discrete energy levels. The energy comes from the Ke and Pe of the electrons. Now, you also know that your electrons are able to jump from a lower energy level to higher energy level, and then subsequently from higher energy level back to lower energy level, right? So now what we want to talk to you about here is what happens to an electron that is orbiting around a nucleus that how to say what we want to talk to you about now is what happens to an electron that is orbiting around a nucleus when it absorbs a photon. Okay, the photoelectric emission that you learned before this was you have photons, and the photons are absorbed by the electrons. If the electron absorbs the photon and the photon is enough energy, the electron will just escape. These electrons here are not necessarily the electrons orbiting around your nucleus. This could be your free electrons that have already broken free from your atom. Now we talk about electrons also, but specifically the electrons that are orbiting around, and we are talking about the electrons orbiting around a nucleus. Okay, this one is more like we are talking about the fixed electrons. Okay, so what happens if these electrons absorbs a photon? So the first thing you just need to know is this: when an electron absorbs a photon, it will jump to a higher energy level. Okay, now the electron that absorbs a photon and jumps to a higher energy level, the energy of that photon absorbs must be equal to the difference in the energy levels. or else the photon will not be absorbed. What I mean by that is just simply this. If say you look at the red lines here, where there are two energy levels, negative 4.2 E and negative 3.2 E, the difference in the energies is actually just 1 eV, right? Correct? So say for example, you have two photons, one with 1 eV value and one with 1.4 eV value. So these two photons here, out of these two photons, only the 1 eV value photon will be absorbed, causing the electron to jump from lower energy level to higher energy level. The photon with 1.4 eV here is not equal to the difference in the energy level here, so this photon will never be absorbed. Okay, so the thing here that you just need to know is that electron absorb photon, it will jump to higher energy level, subject to the photon having energy equal to the difference in energy level. Anything not equal to the energy level will just be ignored. Okay, so that part is fine. Yeah, there's also another photon here, 1.6 eV. These two will be ignored because they're not equal to the difference in energy level. Only this one will be absorbed. Okay, so your electrons jump to a higher energy level. Now you also know that when electrons jump to a higher energy level, they tend to be unstable. They don't stay there for long. Okay, so eventually they have to drop down to a lower energy level to a more stable level. So what happens when these electrons drop down to a lower energy level? When your electrons drop down to a lower energy level, okay, when the electrons drop down to a lower energy level, photons will be emitted back. Okay, now the photons that are emitted back will have energy equal to the difference in energy level. Say for example here, I give you these two red lines here, which is negative 2 eV and negative 5 eV. I have an electron at a higher energy level now. It wants to drop down to a lower energy level. So the difference in these two energy level is 3.2 eV. When this electron drops down to a lower energy level, it will re-emit back photons, okay, whose energy is actually equals to the difference in energy levels here. All right. Now, the other thing that I need to highlight to you is this. When electrons drop to a lower energy level, they can do so in a number of ways. If I look at this example here where you have the 4 lines representing 4 different energy levels, and your electron initially started off from here, if it wants to drop down to the lowest energy level to become more stable, it can either do so in one single step or it can do so in staggered steps. This is one way in which it can drop. It can do so in one step like this, or it can do so in staggered steps, in one step at a time. You can drop down like this, like this, like this, or like this, like this. So regardless of how it drops down, as long as it drops down one energy level to another, photons will always be emitted. Okay, so that is the one thing that I think I need to get it clear for you guys. All right, so based on that, let's just have a look at one question that you guys can do. And for that, go to page 14, all right, of your worksheet. Go to page 14 of your worksheet. Yeah, whatever I just explained here covers page 6 all the way to this part. Okay, the emission spectrum and absorption spectrum is just something that I have not explained yet. So this one, don't bother about this one first. I've merely just explained this part. Page 6 and beginning of page 7 for you. All right, now let's have a look at page 7. So go to page 14 of your worksheet. Just go to page 14 of your worksheet. Okay, now number 16, P42. Question 12A. Now, state and effect once in each case that provides evidence for you of the wave nature of a particle and the particulate nature of electromagnetic radiation. So remember just now at the beginning of the lesson, I told you that there are certain things that will tell you wave can behave as particle, particle can behave as wave, right? So you need to know the specific things that tell you that. If you want to prove that a particle can behave as a wave nature of particle here, you need to use electron diffraction to show that. It shows you the evidence that particle can behave as wave. If on the other hand, you want to prove the particulate nature of electromagnetic radiation, meaning to say you want to prove that electromagnetic radiation can behave as a particle, you need to use photoelectric effect. Okay? What on earth is Compton scattering? I have no idea. It's just a marking scheme pointer. Right? But please use this one. This is the most common one and this is the best one to use. Right? Proving that particle can behave as a wave, use electron diffraction. Proving that wave can behave as particle, photoelectric effect. Okay? So that part is fine. Now, 4 electrons energy levels in the isolated atom are shown here. This is your electron energy level. Now then they tell you for the emission spectrum associated with these energy levels, mark with an arrow the transition that gives rise to the shortest wavelength. Okay, now this one is something called emission spectrum. Just know that for your case here, emission spectrum here refers to the fact that you are trying to emit photons. Okay. So in general, this is something I just wrote here. If your arrows point downward, that means this is emission spectrum, meaning you say you're emitting photons. If this one is talking to you about absorption spectrum, that means you're absorbing photons, so your arrow should be pointing outwards. So just know for now that since we're talking about something called emission spectrums, the word emission here already tells you that you are emitting photons. You're dropping down from a higher energy level to a lower energy level. That's why your arrow is pointing downwards. The word emission tells you photons are emitted, and photons can only be emitted if it's dropping from a higher energy level to lower energy level. So when you want to draw the arrow, it will be going downwards. Okay, so for your case here, they ask you mark with an arrow the transition that gives rise to the shortest wavelength. So you know that the difference in the energy level will give you the photon. Okay, the difference in the energy level will give you the energy of the photon, right? So here, difference in energy level is equal to energy of photon. So in your case, they want the shortest wavelength. So E is equals to hc over lambda. Lambda being smallest, that means E is the largest. So E being the largest means the largest difference in energy level. So you will have to draw the arrow from here to here. Okay. Because shortest wavelength would mean largest energy. Largest energy would mean the largest difference in energy level. That's all there is to it. Alright. And then after that, show that the wavelength of the transition in 1 is 4.35 times 10 power minus 7 meter. Show that if you're going from here to here, the wavelength is actually this value. So you know that the shortest wavelength is when your electron jump from negative 0.54 to negative 3.4. The energy of that photon that is emitted will be equal to the difference in the energy level, which is 2.86 eV. Then from there, that is the energy of your photon. You equate it to hc over lambda, you get your answer. 4.35 times 10 power minus 7 meter. Okay. So also go with that. Right, so if you're okay with that, then that one should be fine. Okay. Then nothing else, then we move on to the next page. This one I think I can just really just skip through it. Now state what is meant by de Broglie wavelength. De Broglie wavelength is actually just the wavelength associated with a particle that is moving. This one just copy from your notes, then no issues. Now calculate the speed of electron having de Broglie wavelength equal to the wavelength in B2. This one is just asking you, if you want to have an electron having the same wavelength as this, what is the speed with which it should move? You see here, de Broglie wavelength will tell you that whatever wavelength your particle has is actually dependent on the momentum, which is also in turn dependent on the speed with which it's moving. The faster you move, the wavelength associated will drop. The slower you move, the wavelength associated with it will increase. Okay, so here they're just asking you, if I want to have an electron whose wavelength is equal to this, how fast should my electron be moving in the first place? So you use this equation. Lambda is equals to hp is equals to h over mv. Find out the required speed by substituting all the required values. You know the Planck constant, you know the mass of the electron, and you also know the wavelength you want. So your electron must be moving with 1.67 times 10 power 3 meter per second. Okay. So this part is okay. Then I'll move on to the other part. Continuation of your notes. Okay. So this part I don't need anymore. Right. So this part is fine now. Then after that, I go on to the next part of your notes. Now, I need to move on to your next chapter, the next subchapter, which is emission spectrum. Okay, now emission spectrum. What is actually emission spectrum? Now, before I go to that, yeah, this one I better just rewrite it. Okay, so if you go on to that part of your note, recall that just now initially I told you this, right? Electrons orbiting around the nucleus have discrete energy levels. Okay, I mentioned to you that electrons orbiting around the nucleus have discrete energy levels. Discrete here means fixed or specific energy levels. Okay, now if say you wanted to prove that electrons have specific or discrete energy levels, there are two things that can be used to prove that. Much in the same way when I told you, if you want to prove that a particle can behave as a wave, you will say that you can use electron diffraction to prove that. And conversely, if I wanted to prove that wave can behave as a particle, you use photoelectric emission to prove that. So now here is something else. You want to prove that electrons have discrete energy levels. What can you use to prove that? So what we'll just tell you is that to prove this, emission spectrum and absorption spectrum are used. Okay. To prove that electrons have discrete energy levels, you will tend to use emission spectrum or absorption spectrum to prove this. Okay, that's the reason why you're learning this right now. Okay, because the observations from your emission spectrum and absorption spectrums prove this. Okay, so to prove these emission and absorption spectrums are used observations from this spectrum is evidence that electrons have discrete energy levels. Now I better use a proper term. Have discrete energy levels. Okay. Now, before I go to that, let's just say I give you two elements now. Now, say for example, now I talk to you about, say, now, different elements, you know, different elements have different electron atomic configuration. This one I just need to tell you this one first. Different elements have different atomic configuration. Hence, the electrons have different energy levels. Okay, just know this one first. Different elements have different atomic configurations, hence the electron will also have different energy level. So say for example, I give you hydrogen now. Okay, your electron energy level could be something like this, 1, 2, you know. Say for example, I give you an example, maybe hydrogen probably only has 3 lines for the electron because this one is dependent on your atomic configuration. If let's just say I talk to you about argon, you won't expect the electron energy levels to just be 3 lines, right? Or that they're of the same value. It'll be much different, right? Maybe in the case of argon, your electron energy levels will be something like this, isn't it? So you see this one here, you just need to understand this one first. Different elements tend to have different atomic configuration. So as a result, the electrons have different energy levels. Okay, they're never the same. They are never the same for different elements. They're never the same with another element. Okay, so just bear this in mind first. This is fact number 1. Now, the other thing I need to tell you here is this. When light is passed through a diffraction grating, it will tend to be split into their component colors. It will be split into their component colors. What do I mean by that is this. If you recall from your AS, if I tell you that this one is, say, white light, and then I tell you that this one is your diffraction grating, and then I tell you that this one is your screen, your white light will be split up into different lines like this. Well, what you see here is actually 7 different colors, right? You will have your Roy G beef here. Okay, so the idea here is this: when you pass light through a diffraction grating, it has a tendency to split that light into their component colors. Okay, so you just understand this fact first. Now, if you want to produce an emission spectrum, you need to use a gas discharge tube. What we mean by this is this. To produce emission spectrum, a gas discharge tube containing one element is used. Okay, to produce emission spectrum, gas discharge tube, containing one element is used. What is a gas discharge tube? It looks like this. This one here is your gas discharge tube. Okay, so let's just say that this one is your gas discharge tube. Say for example, I tell you right now, this element in your element contained inside your gas discharge tube now is hydrogen. Okay, so what will happen is that you run current through your gas discharge tube. What will happen is this. In a gas discharge tube, when current is run through the tube, the electrons in the atoms contained in the tube run through the tube. The electrons in the atoms contained in the tube gain energy and jump to higher energy level. Okay, so the first thing you can just say is this: in a gas discharge tube, when current is run through the tube, the electrons in the atoms inside the tube will gain energy and jump to higher energy level. Okay, so in this case here, as I mentioned to you, when your electrons jump to a higher energy level, they will not stay there for long. Okay, the electrons will not stay there for long. They will jump back to a lower energy level. So what you can say here is that these electrons will drop down to a lower energy level, will eventually drop down to lower energy levels, and emit photons. Okay, so the idea here was that if I look at, say for example, now I talked to you about hydrogen, right? You know that once current runs through the tube, the electrons inside the tube will start to gain energy. In your case, it could be that the electrons jump to a higher energy level. Maybe it goes from here to here, and then after that it will drop back to a lower energy level. Maybe it will do so like this, maybe it will do so like this, or like this. So here you see that you're going to re-emit back photons, right? You have one photon here, you have another photon here, and then you have another photon here. Okay, so what you understand was that each of these photons, okay, so each of these photons correspond to a specific energy and hence specific wavelength and color. Okay, so each of these photons that get emitted in the first place, they actually correspond to certain energies, which in turn correspond to certain wavelengths or certain colors, right? So what will then happen is that all these colors, all these photons, all these different colors, all these colors combine together to form a new color, to form a new resultant color. Okay, then after that, when this is run through a diffraction grating, the color is split to component colors. The color is split to its component colors again. Okay, so this part should be okay. When your photons drops, when your electrons drop to a lower energy level, they will emit photons. Those photons correspond to specific energy, hence specific wavelength and specific color. So these all will combine together to form a new resultant color. Because you see here, all your photons here that get re-emitted, they are all emitted at exactly the same spot. So although maybe I can say that this one is red, this one is blue, or this one is yellow, they all combine together. They will give you a new color here. Alright, they will give you a new color from the gas discharge tube. The photons here is light, alright, light of a certain color, certain wavelength, certain energy, but because they're all emitted at the same spot, they combine to give you a new resultant color. So what you want to do here is this. That new resultant color that comes out, you put a diffraction grating, and then after that you put a screen here. Remember I told you that a diffraction grating has a tendency to split any colors into the component colors. The example would be if you run white light through a diffraction grating, you're going to get the 7 different colors out, right? So same thing here. For your gas discharge tube, your electrons jump to higher energy levels, they drop down, they emit photons, but the photons have specific energy, specific wavelength, specific colors. So all of them combine together, all the different colors combine together to give you a new color. So you cannot see what made up the color anymore. So in order to see what made up that color, you have to run it through a diffraction grating. And then this part here, once you run it through a diffraction grating, this part here is where you see your emission spectrum. Okay, this part here is where you see your emission spectrum. Okay, so the final thing you can just probably say here is this. So when this is run through a diffraction grating, the color is split to its component color. So the last thing you can probably just say is this. Since there are specific colors, produced on the screen, this indicates specific energies of the photons, and hence specific energy levels. Therefore, electrons have discrete energy levels. Okay, so here if you use hydrogen, you put inside a gas discharge tube, by right what you're going to get is some sort of emission spectrum which will look like what you see in your notes there, which will look like this. If you run your emission spectrum, if inside your gas discharge tube you put in hydrogen and you run it through a diffraction grating, the emission spectrum you expect to see is just this. I mean, if you print out the notes black and white, you won't be able to see anything, but if you are looking at the screen right now in computer, you see that there's actually 3 lines here. One color here, one color here, and one color here. This represents a certain energy of the photon, which in turn represents a certain this certain colors represents certain wavelengths, certain energies of photons, and then when they represent certain energy of the photons, they represent certain energy levels. Okay, so if you repeat the experiment for hydrogen again, no matter how many times you do, you will always get back that same colors. Okay, if say you go and change the element contained inside your gas discharge tube, you're gonna get, let's say you go and put helium inside and you repeat the same thing, you're gonna get a different emission spectrum. This time you get different lines, different colors. Again, you see the different colors represent different wavelengths of the photon, different energies of the photons, and hence again different energy levels of the electrons. So if you repeat it for all the other different elements, like let's just say argon or mercury, you get very specific patterns, very specific colors, representing very specific photon energies, which in turn means very specific electron energy levels. Okay, so whatever I just wrote here is actually a more detailed explanation step by step. All right, whatever you have in your notes there is actually just like bits and pieces of everything lah. When it comes to emission spectrum, you are not really required to explain the full process. What you're just required to know is that what is so important about emission spectrum? Emission spectrum provides you proof that electrons have discrete energy levels. That's the only key takeoff point from here. And you're only supposed to know what does emission spectrum look like. It's actually just a series of colored lines on a dark background. Okay. This one is November 18P42. There is one part that asks you to describe what is meant by photon. We've done that before. Is this a packet of energy or EM radiation or electromagnetic radiation? Okay. I would suggest you write the terms in full. Okay. Please practice writing your things in full. Okay. EM radiation people would know, but I would suggest you write it in full. Electromagnetic. Okay. Now, describe the appearance of visible line emission spectrum as seen using a diffraction grating. Okay, so they're asking you to describe how would a line spectrum for a visible line emission spectrum look like. How will an emission spectrum look like? Basically, that's what they're telling you. So in your case here, as I mentioned to you, your emission spectrum actually appears as colored lines on a dark background, or colored lines on a mostly dark background. All right, 2 marks here. Colored lines, dark background. That is what your marking scheme said. Now, then you look at part C. Okay. Right, so I think this one is fine. Now, if you look at part C, the lowest electron energy levels in an isolated hydrogen atom are shown in this figure. This is the electron energy levels of the electrons in an isolated hydrogen atom. An electron is initially at energy level negative 0.85 eV. Okay. State the total number of different wavelengths that may be emitted as the electron de-excites. You now have an electron at the negative 0.85 line. So they're asking you what's the total number of different wavelengths that may be emitted as the electron de-excites or loses energy. So the electron now is de-exciting. Okay. It will drop down from a higher energy level to a lower energy level, and in the process it will emit a photon whose energy is hc over lambda. So when they ask you the total number of different wavelengths, they're asking you actually about the total number of different photons that you will get, the different number of photon energies that you will get. Alright, the wavelength here is actually referring to the photon energy. It's related to the photon energy. So in a way, they're asking you how many different photons will you get. Okay. So this one here, you have to do trial and error. There's actually 6. How do you get the 6? If, for example, I started off with negative 0.85, which is here, what are the possible ways in which your electron can drop down to the lowest energy level? The first one is this one. It can drop in one shot. The second one is like this, like this, like this. Okay. Then another one could be like this, or it could be like this. See, these are the possible ways in which your electron can drop down. Okay, so you have 1, 2, 3, 4, 5, 6. These are the 6 possible ways in which your electron can drop down. Okay, so as I written here also is the same. This one is staggered like this, this one is like this. So you see that when your electron drops down from negative 0.85 down to the lowest level, there can be 6 different unique steps in which it can do so. Either it drops down in one shot, either it drops down step by step like this, and something in between. This is also still considered dropping step by step. Maybe it dropped down like this first, then it dropped down like this. Or maybe it dropped down like this first, then it dropped down like this. So any possible number of ways. So you will actually have 6 different types of photons of different energy, hence 6 different wavelengths. When you're talking about the emission spectrum, you are actually, just now I told you the emission spectrum is when the emission spectrum, yeah, I think I will highlight this. If you're talking about emissions spectrum, just know that the lines point downwards. For absorption spectrum, the lines point upwards. Okay, point downwards, point outward. Why we say it points downward is because remember just now I draw for you the line discharge, the gas discharge tube. The way you get your emission spectrum here was through the emission of photons here. The emission of photons here gives you your emission spectrum here, right? So it's emission. You can only get photons when you are dropping down. That's why I say if you see emission spectrum, the lines are pointing downwards. Okay. The appearance of the emission spectrum is caused by the emission of photons. Hence, your lines must point downwards. All right. So this one is fine. Then you go on to the next one. Now, photons resulting from the electron de-excitation from negative 0.85 eV energy levels are incidents on the surface of a sample of platinum. The platinum has work function energy of 5.6 eV. Determine the maximum kinetic energy eV of photoelectron emitted from the surface of the platinum. Now, what they're talking to you about here now is more on the fact that your photons emitted is now incident on a platinum, and then after that they ask you the photoelectrons emitted from the surface of platinum once the photon is incident on it. This one is actually talking about your photoelectric emission. Okay, this is now talking about your photoelectric emission right now. Okay, so what they basically say is that your platinum is here, the electrons, the photons you get from the excitation of the electrons is not incident on the platinum, and this in turn causes emission of electrons. Okay, so when they ask you the maximum Ke of a photoelectron emitted from the surface of the platinum, it is talking about this part. This one is your photoelectron. The electrons emitted from photoelectric emission. Okay, so you want the maximum kinetic energy. Now, you could understand that the maximum Ke is derived from energy of photon, right? Alright. So the maximum Ke is derived from energy of photon. So Ke is highest when photon energy received is highest. Okay, because the time when I explain photoelectric emission for you, the Ke of your electron is actually whatever remain out of the energy of your photon after the part of the energy was used to remove it from the surface of the metal. So whatever balance remaining was converted to your Ke, right? So here I can say this: maximum Ke is derived from the energy of the photon. Your Ke will actually be highest when the photon energy received is the highest. So now you see you had 6 different photons just now in the previous example. Okay, they tell you all the photons resulting from the electron excitation is not incidence on the surface of a sample of platinum. So actually you have 6 different photons here. Okay, you have 6 different photons right now that are coming towards the surface of the platinum, which cause photoelectric emission. So if you want the maximum Ke possible, you need to take the photon with the highest energy possible. So if you look back at your diagram, which one will give you the highest energy possible? So if you recall that I mentioned to you, the energy of your photon is actually the difference in energy levels. So if you want to get the highest photon energy possible, you need to get the largest difference in energy level possible, which is actually from here to here. This one is the largest difference in energy level, right? This one is where you get photon with, maybe I should just write this. This one is actually the highest energy photon that you will get. So you use that value right now. They want you to get the maximum possible Ke. So to get the maximum possible Ke, you need to get the maximum possible photon energy. So you take the difference between 0.85 and 13.6. You know that the highest energy of the photon is 12.75 eV. Okay. And then after that, you know that photon energy is actually equals to work function plus Ke max, which was basically this form of the equation. HF is equals to 5 plus Ke max. Photon energy you already get from here. Work function you already get from here. So you can straight away find out what is your Ke max. It will be 7.15 eV. Now there's no need to change from eV to joules here, because you see, if you look at the equation, this one is, if it is in eV, this one is in eV, obviously this one will also be in eV. The units are consistent. This one you leave it as eV, this one you leave it as eV, obviously your Ke max will also be in eV. There's no need to change from eV to joules here, because you see it does not affect anything. Right, so this part is fine. Then the other one they ask you is, what is the wavelength of the photon producing the photoelectron in part 1? So for the photon that gave you the largest possible Ke, what was its wavelength? all you just need to do is use A equals to HC over lambda, and you get your answer. Lambda is 9.75 times 10 power minus 8 meter. All right. So if you're okay with that, then I will just move on to the next one, which is absorption spectra. Okay, so let me just turn off. Right. For absorption spectra, I think I better just, yeah, absorption spectra I'll have to explain again. This time I think it's better if I just write it on a separate piece of screen. So this one no issues. Then I'll move on to the next part of your chapter, which is absorption spectra. Emission spectra, you already know how is what you expect to see. You expect to see a series of colored lines on a dark background. Absorption spectra is actually the reverse of that. Okay, what you expect to see is a colored background but with dark lines. You will still see lines, but this time the lines are dark, and then your background is colored. Okay, so it's like the opposite of emission spectrum. Emission spectrum, colored lines on dark background. Absorption spectrum, dark lines on the continuous color spectrum. Okay, so what is absorption spectrum in the first place? This one I have to go through this one here for you. Now, let's just go back to the basics. If say I have absorption spectrum, this is for absorption spectrum. Now, if say for example, I give you white light, and then I tell you I run it through a diffraction grating. This one is your diffraction grating, and then I tell you to put a screen here. All right, what you expect to see on the screen is basically some sort of interference pattern with colored with rainbow colors, right? You say this one is your screen here, and then this is your diffraction grating. Once your white light passes through your diffraction grating, it will be split into their component colors. Let's just say that currently your white light contains a lot of different wavelengths, a lot of different colors. So once it passes through your diffraction grating, they'll all be deflected by different angles because they have different wavelengths. So the appearance that you see here is that you get a spectrum, a colored spectrum. Okay, what you see here is a colored spectrum. Okay, similar to this one. If say for example right now I have light, white light that I just passed through a diffraction grating. I know that because this white light here consists of many different wavelengths of light or many different colors of light, they actually combine together to give me this white light here. But the diffraction grating has the effect of splitting them up. Different wavelength would mean that different, if you have different wavelength, that would mean that they'll all be deflected by different angles. So they will be spread out over a certain length of the screen with different colors. So this is what you get. It's a rainbow color because each individual color, each individual wavelength was deflected by different angles. Okay, so this is what you get if you have just white light passing through a diffraction grating with nothing in between. Okay, so the emphasis here I would like to make is this one has nothing in between. Okay, this one here is, you can just think of it as vacuum. Okay, nothing in between. Now, if I repeat this right now, but I tell you in between here you have a layer of cool gas, what do you expect to see here? So if say for example, I have diffraction grating here, same screen, okay, But this time what I tell you is that in the middle here, I have a layer of cool gas. So what do you think would happen? Hey, wait, no. Oh, my mistake. This is not the... No, my cool gas is not here. Sorry. There's nothing here. Okay, wait, no. This one is vacuum. This one is also vacuum. Okay. Now, say I repeat this one again. Say this time I tell you I have white light, but in between, before hitting your diffraction grating, I tell you you have a layer of cool gas. Okay. This one is the layer of cool gas. Your white light passes through the cool gas before hitting the diffraction grating. So when your white light hits a layer of cool gas before passing through a diffraction grating, you will still expect that whatever light that came inside here will be diffracted. Whatever different wavelengths of light you have, it will be deflected differently. So the colors will actually spread out over the screen. But when you have a layer of cool gas in between, and then you look at the pattern that you see here, what you see here is still colored backgrounds. It's a color spectrum, but with dark lights. Suddenly you see that that same light is producing for you a colored background, but there are certain lines that are dark. It looks like this. Okay. Initially, before passing through the gas, it was just like that. But after passing through the gas, you'll notice that certain lines are now there's a certain lines there that are dark in color. So what is that line there? How did it came about? Right? So what I can just tell you is this. This one is the step-by-step explanation. Now, what you can just say here is that the white light contains photons of different energies and hence wavelength. Okay, if your energies are different, your wavelength is different. Okay, then what happens here is that these photons are absorbed by the atoms, by the electrons of the atoms in the cool gas. They are absorbed by the electrons of the atoms in the cool gas and then jump to a higher energy level and thus jump to a higher energy level. Okay, and thus jump to higher energy levels. Okay, so your white light here can be thought of as consisting of many different photons of different energies and hence wavelength. Different wavelength here means different colors lah. But then as you pass through your layer of cool gas here, the electrons of the atoms inside the cool gas will absorb these photons and then they will jump to a higher energy level. Okay, so as I mentioned to you that these electrons, once they jump to a higher energy level, they're not stable. They will have to jump back down eventually, right? So the photons will drop back to lower energy levels, will drop back to lower energy levels, re-emitting the photons. These photons will drop back to lower energy levels and we emit the photons. And this part is the important part. Okay. What I can say here is maybe this is my electron energy level. The one electron here absorbs a photon, for example, or many different photons. So it therefore jumps to higher energy levels, maybe up to here, go from here to here. But then when it wants to drop down, either it drops down like this, like this, like this, or like this. So you will get all those photons back out. You will get back all your photons, right? These are all your photons being re-emitted. Your photons will be re-emitted back once the electrons drop to a lower energy level. So now, here's the thing. This is the thing that is important. The photons emitted are no longer, the photons are not emitted in the original direction. The photons are not emitted in the same original direction, but all the photons are not emitted in the same original direction, but all directions. Okay, so that would mean that along the original direction, certain photons of certain wavelength, certain colors are missing. So when the resultant white light passes through a diffraction grating, resultant white light passes through the diffraction grating, these photons or colors, let me just rewrite it properly. When the resultant white light passes through the diffraction grating, these photons or colors are not present, shown by as indicated by the dark lines. As indicated by the dark lines in the colored spectrum. Okay. So in essence, this is what happens. So I'll just go through the points again. When white light here contains photons of different energies and hence certain wavelengths, certain colors. These photons are absorbed by the electrons of the atoms in your cool gas. They jump to a higher energy level. But then these photons, not this photon, these electrons will drop back. The electrons will drop back to lower energy levels and re-emit the photon. So what will happen is that electron jump now to a higher energy level. It will re-emit the photons again. But now the photons are not emitted in the same original direction, but in all possible directions. What we mean by that is this. This one, you see your light is going from left to right, isn't it? This is what I mean by the original direction. This is the original direction. Okay. So, but you see, when the photons get re-emitted, there's no guarantee that whatever photon that got re-emitted, maybe I better just draw it here. Okay, this one is say your cool gas now. Okay, and this one is your say original direction. This one is your original direction. Okay, so the photons get re-emitted back once the electrons inside the cool gas drop back to a lower energy level, but there's no guarantee that all these photons will come back in will go back in this direction. You see, the photons, when they are re-emitted back, not all of them will be going back along the same direction. What actually happens is that the photons that are emitted are actually emitted in all directions. Some will go here, some will go here, some of them will go here. This is what we mean by that. The photons are emitted in all directions. Okay, so when you have, say, photons emitting in all directions now, along the original direction, certain photons are actually now missing. Certain photons of a certain wavelength and a certain color are actually now missing. So whatever remaining white light that you have after passing through the cool gas is now missing certain photons, certain colors. So you pass it through the diffraction grating, and then the diffraction grating is meant to spread out all the different colors onto a screen here. If the colors are missing in the first place, that color will not show in your colored spectrum. That's why you get these dark lines here. Right? The dark lines here indicate to you that certain photons, certain wavelengths, certain colors are already missing in the direction that you're observing. Okay, that is how you got the appearance of these dark lines here. Right? So the photons are not emitted in the same original direction, but all directions. Along the original direction, certain photons of certain wavelengths, certain colors are missing. When the resultant white light passes through the diffraction grating, these photons are not present, as indicated by the dark lines in the spectrum. Maybe I better reword this. When the resultant light passes through the diffraction grating, the dark lines in the spectrum, yeah, maybe I just erase this. Maybe I rewrite this. When the resultant light passes through the diffraction grating, the dark lines on the colored spectrum represent the photons or color that are missing, not in the not emitted in the direction. Okay, the dark lines on the color spectrum represent the photons or color that are missing. All right, because they were emitted in a different direction. Okay, so this one will be better. When you see when the resultant white light passes through the diffraction grating, the dark lines on the color spectrum represent the photons of color that are missing, because they were emitted in different directions in the first place. All right. So if I want to give you some example here, maybe I can just tell you, maybe this one was red, this one was blue, this one was yellow, and then this one was green. Okay. Say for example, red was not emitted back in the same direction. Red instead was emitted here. And then after that, I tell you maybe green was emitted here. The only ones that were emitted back in the same original direction could be probably blue and yellow. So when you pass this through the diffraction grating, you're still going to get the blue and yellow, but you're not going to see the green and the red because they were not in the same direction in the first place. Okay, so that is what absorption spectrum actually is. The dark lines are due to the fact that your photons re-emitted are not in the same direction. They were emitted in all possible directions in the first place. Okay, so whatever that is here is actually describing that. This little thing that is here is describing this case here. The little other part after these nodes is talking about light from the sun passing through cool gas before hitting the earth, and then if you run that light while on the earth you see dark lines on the color spectrum. It is still based on the same concept. When light from the sun passes through space before being incident on earth, it will pass through space. Space has some pockets of cool gas or something like that, or even through the atmosphere. Your atmosphere itself has cool gas. So when the light passes through those cool gases, this thing actually happens. Your photons are emitted back in different directions. So if you go and take sunlight and you pass it through diffraction gating, you will again see this same pattern. Okay, colored background but with dark lights. All right, so whatever that is being described here, it's actually talking about light from the sun passing through cool gas before you diffract it with a diffraction grating. It is still based on the same concept as I explained here. All right. So with that one is absorption spectrum. So we might as well just go to some questions. Go to page 16. Yeah. Go to page 16. Get an idea of what I mean. Have a look at page 16. Mark 17 Q42. Yeah. It cannot. Wait, let me. Sorry, I had to stop the screen share for a while because something is wrong. Okay, wait on. Mark 17 Q42 question 10. Okay, now start. Now, still as remember photon, we've just done this. I'll just keep this one. Alright. Like photon is just a packet of energy or EM radiation, electromagnetic radiation. Now, part B is the one I want to talk about. Light in a beam has a continuous spectrum that lies between the visible region. The photons of light have energies ranging from 1.6 eV to 2.6 eV. The beam passes through some hydrogen gas. It then passes through a diffraction grating and an absorption spectrum is observed. All the light absorbed by the hydrogen is re-emitted. Explain why dark lines are observed in the absorption spectrum. Okay, so this is actually what I was just talking to you about, not the little case here where I talked to you about light. Then after that you have hydrogen gas here, which is actually your so-called cool gases lah. Alright, then after that you have your diffraction grating, and then this is your screen. So what you get here is colored background with dark lines. So they're asking you right now, why is there dark lines observed in the absorption spectrum? So as I mentioned to you, was because the photons, or rather the light, is actually emitted in all directions. Whatever light or photons that were observed or absorbed here, they did not all go back in this direction. Rather, they went here, 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 here. A portion of it went in different directions, not in this direction. So the reasoning was this one. You can just say this one. The light is emitted in all directions. Only part of the emitted light is in the direction of the beam. Or if you want to be more specific, you can just say that the light photons are emitted in all directions, or only part of the emitted light photons is in the direction of the beam. Okay? The keyword is you needing to talk about that photon being emitted in all directions. That is usually the point here that you need to talk about. Okay. Now, for part 2, some of the energy levels of electron in the hydrogen atom are illustrated here. The dark lines in the absorption spectrum are the result of electron transitions between energy levels. On figure 10.1, draw arrows to show the initial electron transitions between energy levels that could give rise to the dark lines in the absorption spectrum. Okay, so this one for the hydrogen atom, this is the electron energy levels. And then they tell you the dark lines here are the result of the electron transitions between the energy levels. Your electron jump to a higher energy level, as I mentioned. Your electron jump to a higher energy level, but then after that, it will eventually drop back down. And then you will emit the photons. But the photons do not get re-emitted back in the original direction, but other direction. So that is what causes your dark lines. So this one is what they're talking about. Alright, the dark lines in the absorption spectrum are the result of the electron transitions between the energy levels. What they did not tell you is that when the electrons drop back down, they get re-emitted back in different directions. That is what actually causes you the dark lines. Okay, so draw the lines. Draw arrows to show the initial electron transitions between energy levels that could give rise to the dark lines in the absorption spectrum. Now, what are the possible transitions that will give rise to the dark lines here? Now, if you look at your question, they really told you the light beam here that you have photons with energy ranging from 1.6 eV to 2.6 eV. Okay, so that will mean that whatever electron transition you have going up and then going back down, which then got lost in different directions, must only be in this direction, must only have values in this range. Okay, whatever energy of photons that came in has this value, has this range only. So it follows that whatever photons that get re-emitted back will also still have that same range. So they're asking you to show the electron transitions that could give rise to those dark lines. Basically, they're just asking you to show what are the possible photon energy that could came out of it, that could have come out of it and got lost. So from here, you just do try and error. Which are the energy level transitions that will still give you this range? It's actually only these two. If you want to do try and error here, if you have your calculator with you, you will see that this one here, maybe I use a different time. You will see that this one here, 13.6 minus 3.4 is 10.2, right? Isn't this out of range already? So this part I cannot consider. Then if say I consider here to here, 0.85 minus 0.54, it is 0.31 eV. It is smaller than this, isn't it? So this one is also out of range. But if I'm talking about from here to here, 3.4 minus 1.51, this is 1.89 eV. So it's within range. If I talk about 3.4 minus 0.85, it is 2.55 eV, so it's within range. So these are the only two possible transitions that may give me the dark lines. But not this one, because the photon energy is out of range already. Okay. So that's that. Then after that, they ask you to calculate the shortest wavelength of the light in the beam. Okay. What's the shortest wavelength of light in the beam? Now your beam is talking about this one. When they ask you the shortest wavelength of light in the beam, you do not necessarily refer to this. You have to refer to this. Okay. Because the beam itself, they're not asking you the shortest wavelength of the light in the, maybe I better reword my statement properly. When they ask you to calculate the shortest wavelength of light in the beam, it's talking to you about this side. It's talking to you about here. Okay, This one is talking to you about this. What's the shortest wavelength of light in the beam here? Okay. So here you see that your energy of photon is 1.6 to 2.6 eV. E is equals to hc over lambda. The shortest wavelength will usually be the one with the highest energy, so you have to take the 2.6 eV straight. You will not be using the ones here. This one are the re-emitted photons. Okay. Specifically, if you're talking about the re-emitted photons, this one will be, these are just the re-emitted photons. But there are still other photons also that will pass through. What do I mean by that is this now. If this one was your hydrogen gas, you think of it this way now. Your energy of photon is 1.6 to 2.6 eV. Out of the photons here with this range, you see the photons that are inside this light beam here will have energy from 1.6 to 2.6 eV. There's a lot of photons with different energies, but they'll be from this range. But out of this group of photons, only the one with 2.55 eV and only the one with 1.89 eV, when it passes through the hydrogen gas, will actually cause the electron to jump up and then drop back down, and the photons are re-emitted. The other photons with different energy here, let's just say maybe I have a photon with energy 1.7 eV, and then here I have a photon of 2.58 eV. This one and this one, when it passes through the gas, it will not be absorbed. It will just pass straight through. Because remember, I told you that electrons will only absorb photons that are equal to the difference in energy level. Photons that are not equal to the difference in energy level will just be ignored. It will not be absorbed. Okay. So like in your case here, when they ask you to calculate the shortest wavelength of light in the beam, they're asking you for the beam as a whole. They're not asking you about the shortest wavelength of light that was re-emitted. If they ask you the shortest wavelength of light in the beam that was re-emitted, then you will actually need to use this one. Okay, so be careful about the wording. They're not asking you the shortest wavelength of light in the beam that was re-emitted. If they're asking you that, then this one you will use 2.55. But now they're not asking you that. They're asking you about the whole beam as a whole. So for the whole beam itself, you have 1.6 to 2.6 eV, right? So use that energy 2.6 eV change to joules, and then find out the wavelength. You get the answer as 4.78 times 10 power minus 7 meter. Okay, so if that one is okay, then you can have a look at page 18. This one should be the last one, so I can move on to the other questions. Now have a look at page 18 of your worksheet. This one I think is the 8th, sorry. Have a look at page 18 of your worksheet. This one is I think the longer question. June 17 P41. Okay. Now you have a beam of light that consists of continuous range of wavelengths from 420 nanometer to 740 nanometer. The light passes through a cloud of cool gas as shown in figure 11.1. The spectrum of light emerging from the cloud of cool gas is viewed using a diffraction grating. Explain why the spectrum contains a number of dark lines. Now this case here is exactly the same like just now. Light containing photons of different wavelengths, different energy passes through your cool gas. Whatever light that came out of it is passed through a diffraction grating. They put a diffraction grating here. Then after that they have a screen here. And then what they saw was that your spectrum, what you see is a spectrum with dark lines. Okay, or rather colored spectrum with dark lines now. Okay, same thing, same case as before. They're still talking about the same thing. So they're asking you, why does your spectrum have dark lines? Then why does it contain a number of dark lines like this? Alright. So this one is same question as before, but that one was just a simple statement. 1 mark would do. That one was just a small. This question is not long. It just has 1 mark there. So you just needed to state this. The light photons were emitted in all directions. But this same question is asking you to explain the appearance of the dark lines, but they give it more marks. It's 4 marks. It's 4 times more than the previous question. So you have to explain much more things. So you have to say that the electrons in the gas atoms interact with the photons of light. The photon energy causes the electron to move to higher energy levels. The photon energy absorbed must be equal to the difference in energy of the electron energy levels. When these electrons return to their original energy levels, photons are emitted in all directions, causing the appearance of those dark lines. In the previous question, this was just what they wanted. But now with a 4 mark question, you have to explain a few steps back what is actually happening. Okay. Right, so to copy that, if you don't have time to copy that, you can copy it from Google Drive later. If you look at part B, some of the electron energy levels of the atoms in the cloud of gas are represented in figure 11.2. They tell you light of wavelength 420 nanometer has photon energy of 2.96 eV. Calculate the photon energy in eV of light of wavelength 140 nanometer. There are 2 ways to go about this. Either you want to use ratio or either you just want to use direct straight calculation. If you want to calculate the energy in EV of light of wavelength 140 nanometer, you can just straight away use E equals to HT over lambda, calculate out the energy in joules, then change the energy in joules to EV. This one is fine. Or if you want to complicate things further, you can use ratio. E is equals to HT over lambda. H and C here being constant, that means E is inversely proportional to lambda. E2, E1 is lambda 1, lambda 2. Then after that, you solving the values, you can still get the same answer. But I think this is also possible if you are so used to ratio. But if you're not used to that, you can just straight away calculate from here. All right. You will get your answer as 1.68 eV. So no issues here. The only other thing here is if you look at part 2, use data from 1 and your answer in 1 to show on figure 11.2 the changes in energy levels that will give rise to the dark lines in A. Okay. So it's again similar to that question that we just done just now. When you have light whose photon has energy or wavelengths within this range, out of this range, what wavelengths or what photon energy actually gave rise to your dark lights? What photon energy actually were re-emitted in the different directions that gave you back your dark lights? So simply put, if you know the range is what, 420 nanometer was this one, right? 420 nanometer was 2.96 eV. So 140 nanometer is 1.68 eV. So if your light has wavelength 420 nanometer to 740 nanometer, it means that the photons have energy between 1.68 eV to 2.96 eV. So out of this range, which one actually caused your dark lights? Which one was actually absorbed by the electrons and got re-emitted in different directions? So you just draw to try and error again. See which one is the range. Same thing as before, there are some things you can normally start off with first. You always try to look at the biggest range first from the bottom and the smallest range at the top. What I mean is this. If this one you see, you can do try and error, you can see that 13.6 minus 3.4 is already 10.2. This one is out of range already. And then you see this one here, 0.54 minus 0.38 is 0.16 eV. This one is also definitely out of range. So this one you don't need to consider anymore. This one you don't need to consider anymore. So you just need to consider this part. And then you see, look. You see this one, I consider this one I will get 1.9 eV. This one I'll get 2.55. This one I'll get 2.86. Now I will not consider this because you see 1.5 minus 0.54 is 0.96 eV. This one is again out of range, so it is out. So only this one is in. Okay, these are the possible photon energies that were absorbed and were re-emitted in different directions. Okay, I better just write it properly for you. This one is 1.5 eV. This one is 0.5 eV. This is 0.8. Wait, sorry, my mistake. This is not what I was talking about. This one is 1.9 eV, 2.55 eV, 2.86 eV. These are the photons that were absorbed and re-emitted in different directions. Okay, these are the three photons that were observed and re-emitted in the different directions that could give you your dark lights. Okay. In different directions to give the dark lights. So that part should be fine.